All right, hi AP students, welcome to your AP weak acid strong base titration and buffer AP question walkthrough. The first question we're going to go through in this problem walkthrough is going to be the last portion of AP question number 2, short FRQ, ending on page 9 regarding buffers. So this second portion, or like last, I don't know, 30% of this question is actually a great conceptual review on buffers as well as an AP question. And then we will hit up a full AP free response on weak acid strong base titration. So let's go ahead and begin. So you might want to take a moment to reorient yourself on this problem where we were looking at specifically the acid HOCl, hypochlorous acid. And we did a comparison initially. We drew a Lewis dot diagram. We used our understanding of how structure determines function, how the structure of our acid determines the strength of the acid. We determined the KB, and we also solved for the presence of OH, okay? And then we came to this portion in our free response where it is talking about buffers. And we know a buffer is a solution whose conjugate species is present in solution alongside the original species. So what we would say is that means that those two species, the conjugate pair species, are in equilibrium with one another. Hence why we see buffer solutions only be present and possible with weak acid or weak base involving mixtures, because only weak acid and weak bases demonstrate equilibrium chemistry. So a buffer solution is prepared by dissolving some solid NaOCl in a solution of HOCl at 298 Kelvin. The pH of the buffer solution is determined to be 6.48. So quick note, when you see this, okay, you're like NaOCl, HOCl, isn't that a common ion effect? Not really. Here we're, like kind of in a way, but here we're more looking at it. NaOCl would dissociate into Na and negative OCl, right? OCl anion. And then you have HOCl present. So more than just the common ion effect, which totally is one way of looking at it. It's totally parallel in thought process. What you have here is the presence of the conjugate species, the protonated and the deprotonated version of a species. So that's what we're going to be emphasizing here. And you're even told how to think about this and when they said buffer solution. So you should be thinking in the context of buffers, not necessarily common ion. Okay, so we're asked to calculate the value of H3O plus in the buffer solution. Well, you know that the pH is 6.48. And so this is a nice freebie question. If I know pH equals 6.48, okay, then I know that my solution has a concentration of H3O plus of 10 raised to the negative pH. So I get a value of, okay, 10 raised to the negative 6.48. And I get a value of 3.3 times 10 to the negative 7 molarity for my concentration. And let me move this over because I didn't leave myself enough room. Molarity. So the second part is indicate which of species of the conjugate pair, HOCl or OCl, is present in the higher concentration of the buffer. So the buffer is, remember, in equilibrium, and we can have the equilibrium position be shifted in favor of one direction versus the other. So we want to figure out, okay, where does this buffer solution find its equilibrium? Is its equilibrium found in favor of the acid species, or is it found in favor of the conjugate base species? So what we need to recall is that oftentimes a question will ask you to pull from the portion right before it, especially if it's under the same subheading. And two, it'll often refer you back to the data. So you just solved, well, I guess I should start by saying this. What is the equation that allows us to even determine a ratio of concentration? Well, you should automatically think, well, one of the only equations I know that actually puts a ratio between the conjugate and the original species is the actual K equilibrium, and specifically the Ka, because we're talking about an acid. You could go from Kb, but I would go from Ka, okay? Partly because our data is given in terms of acidic values, so I would take that as a hint in the prompt. And we see that Ka we know is equal to H plus OCl minus and all over HOCl, the protonated version. And we know, of course, Ka is the equilibrium constant. So we know that this is telling us the concentrations, the relative concentrations at equilibrium for the weak acid. So this is how we know that this is the correct equation, mathematical relationship to use between the two conjugate pair species. Because one, we're asked, well, and buffer solution, which is higher. Well, we're assuming, because they didn't tell us otherwise to think about it being at the beginning stages or the end stage, we're assuming that we're talking about a point of equilibrium. And when the buffer solution is present, it will establish its own equilibrium. Okay, what will be the relative concentrations at equilibrium? That should be an immediate cue to use K value. Two, it's also one of the only equations that actually allows us to put a ratio between the two concentrations, okay? You might think immediately to yourself, oh, Henderson-Hasselbalch, but here's the thing, Henderson-Hasselbalch equation asks you to solve for pH and pKa. So you could technically put it into the Henderson-Hasselbalch, but it would actually be a lot more work because in the end, you really just want the ratio. And you did just solve for H3O plus. So that's also another big hint that in the previous problem, you solve for that value theoretically at equilibrium. Because again, the prompt didn't specify that it was at the beginning or past equilibrium. We're assuming stability in the buffer solution. So then what you do is you plug in your known facts. You go back. Oh, sorry, 1 second. Okay, so you go back to your data and you know Ka for HOCl. And you just solved for H plus, okay? So you plug in what you know. Well, I know that Ka is equal to 2.9 times 10 to the negative 8th, according to the data they gave me. And that's going to equal the concentration H plus, which by the way, I just solved for my buffer solution. I was given the pH, therefore I could solve for the concentration of my H3O plus or my H plus ion present at equilibrium for the buffer solution. Okay, and I get that at 3.3 times 10 to the negative 7. Okay, and then I'm left with, well, I still don't know, I'm solving for the ratio of concentration between OCl minus conjugate base and HOCl present in the buffer solution theoretically at equilibrium. So what you notice then is if you did a little bit of algebraic manipulation, you actually get a ratio. You get 2.9 times 10 to the negative 8th all over 3.3 times 10 to the negative 7th equals, okay, the ratio between OCl minus concentration present in the buffer solution and HOCl concentration. And so what you see then is that the value of HOCl, that is, well, the value put equivalent in the fraction to HOCl is a higher value. It's only times 10 to the negative 7 power, whereas the OCl minus value that's equivalent to it as the numerator is put to the power of 10 to the negative 8th. So what that tells you is that according to our K equilibrium for the acid, okay, of the buffer solution, we see that the conjugate, okay, species OCl minus is in lower, okay, concentration than the original acid protonated species. Okay, according to our Ka equilibrium constant expression manipulations. That was a really long term. Okay, so let's go over question number 4 now on page 12. Okay, so here we're told that we have propanoic acid and it's a carboxylic acid, which we know is a common weak acid, that reacts with water according to the equation above. At 25 degrees Celsius, the pH of a 50 milliliter sample of 0.2 molar propanoic acid is 2.79. Okay, so first step, identify a Bronsted-Lowry conjugate acid-base pair in this reaction. Clearly label which is the acid and which is the base. So you have two options. You could say that we have pair number 1. Okay, let me put this in black. Okay, this is going real basic. They're starting off real kind to you guys, giving you points, winners. Pair number 1 that you can mention is the relationship between the propanoic acid, deprotonated versus propanated. So this would be CH3CH2COOH, which acts as the acid, okay? And then we have CH3CH2COO minus carboxylate conjugate base. Okay, you also totally could have selected this relationship between water. It is a shorter writing process. So the the base is water, and the conjugate acid is the H3O plus hydronium atom. Okay, so either one would have won you the point. And then we're asked to determine the Ka value for propanoic acid at 25 degrees Celsius. So what you have to realize is, in order to determine the Ka value, you are given pH at equivalence. Okay, so this is the pH at equivalence. You are also given the original molarity sample, right? So at 25 degrees Celsius, the pH of the 50 milliliter sample of 0.2 molar is 2.79. So we're assuming the pH of the solution, unless otherwise told, is a pH at equilibrium. So what you're going to want to notice is when you set up, you're going to definitely have to use, this is a K equilibrium type of problem, a Ka problem, where you're given the initial concentration and you're given the equilibrium value, though you have to do a little bit of mathematical manipulation to find it. You're given pH at equilibrium, and then you have to figure out what Ka is. So what you need to consider then is you want to set up an ice table, okay? So I have CH3CH2COOH reacts with water, liquid, in equilibrium with its conjugate. And H3O plus, it's going to be ICE. Okay, and we know that the liquid doesn't really matter, and we start filling it in. Well, I know that from the problem, I have a 0.20 molar, okay, which I don't need to include, 0.20 molar initial concentration. According to my prompt, my pH at equilibrium is equal to 2.79, which means that my acid concentration at equilibrium is equal to 10 raised to the negative 2.79, which means that I have an acid equilibrium of value of 1.6 times 10 to the negative 3 molarity. So then I plug that into 1.6 times 10 to the negative 3. Then I use my stoichiometric ratios to determine the concentrations at equilibrium for my other conjugate base species produced, my other ion produced. Remember, Ka is simply the product of the ions produced over the original concentration, right? So I'm plugging in the ion concentrations essentially at equilibrium. I'm also going to, to complete the table, plug in the change. We are in a 1-to-1 ratio, which for most acids, unless they're polyprotic, we are always in a 1-to-1 ratio of change. And of course, we have a negative change here in a 1-to-1-to-1 ratio. And that means that when we do the math, okay, we see a value of, okay, let's see, 0.20 divided, or minus, sorry, 0.20 minus 0. Let's see, let's do my math. 0.20 minus 0.0016. That gives us a value of 0.0016. 0.1984, which is basically the same thing, but whatever. Okay, you subtract, you're adding here, and you fill in the table. Okay, so now that you have your values, this is again I think I mentioned this type 3 problem of equilibrium are like your dream problems because they're just basically plug and chug. Now I take my equilibrium values, concentrate for the concentrations of each species, and I simply plug into my Ka expression, and I know that Ka is going to be equal to, okay, the concentration of H3O plus at equilibrium times the concentration of my other ion, my conjugate base ion produced, CH3CH2. Oh my gosh, I definitely did not leave myself enough room. COO minus. Oop. COO minus concentration all over the initial concentration of my weak acid, propanoic acid, CH2COOH. And when I plug in these values, okay, I get that's equal to 1.6 times 10 to the negative third squared, because it's each ion had the same concentration due to its 1-to-1 molar ratio, all over my solve 0.1984. And what I get is according to sig figs, which is based off of my 2 digits after my pH value and my 2 sig figs of my molarity value given, I get that my Ka is equal to 1.3 times 10 to the negative fifth. Okay, which makes sense as it's in times 10 to the negative because it's a weak acid. So it should have a pretty weak Ka value. Okay. So next part. So for each of the following statements, determine whether the statement is true or false and then explain. Okay. So the pH of a solution prepared by mixing 50 milliliter sample of the 0.2 molar propanoic acid with a sample of 50 milliliters of 0.20 molar NaOH is 7. Okay. Automatically, you should be like, no, because the only time that we get equivalence, because essentially this is talking about the pH once equivalence is reached, right? Equilibrium equivalence. The only time we get pH is equal to 7 is only when we mix a strong acid with a strong base. But here we have a weak acid, weak base. Okay. So weak acid, strong base mixture. So we know that at equivalence will favor base, partly because the weak acid creates a buffer solution where you have conjugate base present. So you not only have a conjugate base present, you also have a strong base present. So you know then that the equilibrium is shifted to a pH higher than 7. So this statement is false, okay? Because the weak acid produces a conjugate base, okay, that shifts the equilibrium, okay, toward a pH greater than 7 at equivalence. Okay. Or you could even say it just shifts the equilibrium toward a pH greater than 7. You don't even have to include the at equivalence. That is totally an optional statement. Okay. So, okay. And if you wanted to, the AP does offer you, like, you could have also argued this with a graphic about how the conjugate base has its own equilibrium with water where it produces, okay, more OH minus ions. So you could have also written this as a chemical formula where my conjugate base that is produced from my weak acid now has its own equilibrium with water, which by the way is a type of hydrolysis reaction. Okay, an ion plus water. And it has its own equilibrium producing protonated, okay, regenerated protonated acidic propanoic acid and H2O HO minus plus OH minus, which of course is the source of increased base behavior, increased base species present. Okay. The real reason that CH3CH2COO minus is a base is because when it hydrolyzes or undergoes a acid base equilibrium reaction with the water, it actually produces the OH minus. Okay. Either way that you approach this is totally fine. So 2, if the pH of a hydrochloric acid, which is by the way a strong acid, is the same as the pH of a propanoic acid solution, then the molar concentration of the hydrochloric acid solution must be less than the molar concentration of the propanoic acid solution. So here, what we're seeing is that we're comparing a weak acid, propanoic acid, right? CH3CH2COOH versus a strong acid, HCl, okay, hydrochloric acid. And we're told that they have the same pH. Therefore, the molar concentration of hydrochloric acid must be less than the molar concentration of propanoic acid. And the question is, did that make sense? Well, if we have a pH that is equivalent, an equivalent pH means that the presence of H3O plus is equal for both species. Now, that means that both species have to be producing an equal amount of H3O plus. So what we know then is for strong acids, they ionize completely, complete ionization. Okay, they ionize completely. There you go, complete ionization. But weak acids only partially ionize. So they're less effective at producing ion. So we would say then that the statement is true because strong acid, HCl, ionizes completely, and while, I've put while, weak acid, propanoic, God, I hope I spelled that right, propanoic ionizes partially, and therefore requires a higher concentration to produce the same amount of acid, okay? Or of H3O plus. Maybe I should put that specifically, of H3O plus concentration, okay? So that is the first subsection of this FRQ. Let's move on to the next one. We're going to finish out this whole thing. So let's move on to the next part and final part where we have a sub prompt within it. A student is given the task of determining the concentration of propanoic acid solution of an unknown concentration. Okay, so we know that's our analyte. Our titrant is a 0.173 molar solution, okay, that's available, okay, of NaOH. The student uses 25 milliliters to deliver the propanoic acid solution to a clean, dry flask. After adding an appropriate indicator to the flask, so one whose pH of endpoint lines up, parallels with the pH of the equivalence point, and the student titrates the solution, reaching the endpoint, i.e. equivalence, after 20.52 milliliters of the base has been added. Calculate the molarity of the propanoic acid solution. So the first thing is you need to, in order to calculate the molarity of the propanoic acid, you need to figure out, well, what were the moles of NaOH used? And then how does that stoichiometrically reveal the moles of acid neutralized? So we're told that we used 20.52 milliliters, which is of course equal to 0.02052 liters of NaOH. Okay, and we know that the concentration of that was, I'm going to highlight this whole thing and shrink it. Okay, the concentration of that is going to allow us to turn that into a math tool and determine the moles used. So given that 0.02052 liters of NaOH with a molarity of 0.173 moles per liter, molarity of NaOH was used, we know that the moles of NaOH, okay, was 3, let's put it inside sig figs in scientific notation, 3.55 times 10 to the negative 3 molarity of NaOH was consumed. And I know I'm not looking at a polyprotic acid. So I know that for most of these, this is a 1-to-1 ratio. So for every 1 mole of NaOH consumed, okay, I neutralize 1 mole of the acid, which I don't want to write out the full name, for every 1 mole of NaOH, okay? And so that means that we also have at equilibrium, and I don't know why I write molarity, silly me, it's moles. Moles, okay? That means that I neutralized, and I'll put this in green, 3.55 times 10 to the negative 3 moles of acid. Okay, so now that I know how many moles of acid were neutralized, I can go back to the prompt and say, well, I was told that I used, let's see, I was told that I used 25 milliliters, okay, of the propanoic acid. So what was the molarity of a 25 milliliter solution that had 3.55 times 10 to negative 3 moles of acid? Well, that is an easy mathematical process. You do 3.55 times 10 to negative 3 moles all over the liters used in the sample, which was 25 milliliters, which is equal to 0.025 liters. And you get your units for molarity, moles over liters, and you find that the concentration of your analyte solution, propanoic acid, is 0.142 molarity. Okay, and that, all right, is your answer. Okay, last part, D. The student is able to redesign the experiment to determine the concentration, okay, of a butanoic acid solution instead of a propanoic acid solution. For butanoic acid, the value of pKa is 4.83. The student claims that a different indicator would be required to determine the equivalence point of the titration. Based on your response, do you agree or disagree? Okay, so first of all, we need to consider that they gave us pKa. When you look at pKa, you need to remember that the higher the pKa, okay, the worse the acid. Okay, so that's something that you want to keep in mind. So when you look at R2, we're comparing propanoic versus butanoic acid. And you're given pKa. So what you might want to consider doing is comparing the pKa's of the two, because you need to determine if you're going to require a different indicator, which means you're going to have a different range of pH for your equivalents. So butanoic was given to me from the prompt that I have a butanoic pKa of 4.83. Well, I've solved for, in part B, the Ka of propanoic acid. So from part B, I know that propanoic acid has a Ka of 1.3 times 10 to the negative 5th. 1.3 times 10 to the negative 5th is the Ka, sorry, of propanoic acid. Okay, propanoic. So the pKa is going to be that negative log of 1.3 times 10 to the negative fifth, and that's going to equal, okay, 4.89. Okay, so this means I have a pKa of 4.89 for propanoic acid. These are incredibly similar. So due to the similarity of the acidic behavior via pKa comparison, we could say safely that we actually disagree with the student. Because these similar pKa values indicate similar acidity and thus equivalence point. Okay, especially if we're talking about a buffer range is between 2, right? A buffer range is always within a 2 logarithmic unit. And since these do not range farther than 2, you can safely say that the equivalence point is within the range of 1 buffer or 1, sorry, not buffer, indicator. Totally meant indicator. Since the indicator, okay, goes range across a pH of 2 units or a pKa of 2 units, because technically at equivalence, okay, right, we can make all those comparisons. This is both weak acids, pKa equals pH. Anyway, all that stuff. We could safely say that the indicator being used for propanoic acid would sufficiently indicate and align within a correct and reasonable range for the equivalence of butanoic acid, okay? So I should have probably written all that down instead of just spoke it. And thus the equivalence point and thus equivalence point for both acids should be both equivalence points for both acid should be how do I say this? Properly indicated should be accurately indicated with the same indicator. Oh my gosh. With the same indicator. Okie dokie. All right, that's the end of that one. As you guys study, don't forget, I'm not covering every single AP question. So make sure you head back, finish out some that we didn't finish. Make sure you've head back and done the conceptual. It's a really great warm up for these problems. And of course, these AP questions don't cover everything either. So make sure you're really understanding the process of the types of problems you can encounter from our notes. So best of luck. Good job, everyone. Bye.